We can start in 2 minutes. It's going on the live. It's going live on YouTube.
Yes, I've actually got an indication that says it's now streaming live, so it's already on.
Oh, yes, we can start.
Okay. Good morning, everybody, and welcome to the EPSRC Network Plus Digitalized Surface Manufacturing Network webinar. And the title of today's webinar is PVD Thin Film Coatings, the Enabling Technology for Sustainable Solutions and Carbon Footprint Reductions. My name is Professor Peter Kelly. I'm from Manchester Metropolitan University, and I run the Surface Engineering Group here. Just a couple of bits of housekeeping. If anybody is cut off during the webinar, please just rejoin. And if anybody has any questions, please add them in the chat box and we'll go through them at the end of today's presentation. So with that in mind, it's a great pleasure to introduce Ton Hertmans as our speaker today, or this morning, because there is another webinar this afternoon. Please watch out for that one. So Ton Hertmans is a PhD from Sheffield Hallam and also EMBA in Ohio State. He's worked in vacuum coatings since 1990. He's worked with both Hauser Techno Coatings and Iron Bond in both Europe and North America. And he's ideally placed to address the title of today's presentation. So Ton, over to you, please.
All right. Thanks for the nice and kind introductions, Peter. I will give my best. Let me share the screen, of course. Here we are. So thank you all for being here and showing interest in my presentation. The title of the presentation, as you can see, PVD thin film coatings, the enabling technology for sustainable solutions and carbon footprint reductions. I take the chance to introduce the company over a couple of slides. Don't worry, there's only a few. Iron Bond is the company I work for, and I'm the CTO of the IHI Iron Bond group worldwide, responsible for the technologies and technology development. Iron Bond is part of the Japanese company IHI. It's publicly traded at the Japanese stock market, and it's a large industrial conglomerate having companies in many different industries. Iron Bond is a PVD and PACVD job coating service supplier, and we have a sister company that's actually making PVD and PACVD coating equipment. I will get into that, what it stands for, PVD and PACVD, in a minute. If you look at Iron Bond coating network, we have 35 coating centers spread over the world. Sorry. And as you notice, they're all ISO certified, and depending on what type of business we are in, we have dedicated additional quality certifications for automotive, aerospace, medical, etc., and environmental. Iron Bond has an internal segmentation of the business because we have so many different customers with all their own requirements and expectations. You see here we have two categories that is related to making parts, cutting tools and forming tools. You are going to see some examples of sustainability use in that territory as well. But also we coat components that you might see in your daily life and that you are using maybe without knowing at this point in time. That's automotive, medical, what we call industrial components, and aerospace and decorative components. And we started about 5 years ago also in the hydrogen economy, fuel cells, and electrolyzer applications. Short word on PVD and PACVD coatings, if you're not familiar with this. PVD stands for physical vapor deposition. We have parts that are on a carrier in a machine, and it's a vacuum coating machine. So in order to create a vacuum, we have vacuum pumps to get that state. Then we have defined gases coming in the symbolic way on the top over here. What we actually do, we evaporate metals into a metal flux. You see it here on the right in this cone for, let's say, so-called circular evaporator, and it sprays on the parts, and we form a coating because the metal flux will condensate on the surface of a part. Depending whether we use just an inert gas, it will remain a metal as is, but we can also react it to a so-called ceramic material, a nitride, a carbide, a carbonitride, or an oxide, and to form different materials on the surface of these parts. There's different ways to get a metal in a metal vapor flux. That can be either so-called cathodic arc evaporation, arc sources in short over here, or magnetron sputtering. For today discussion, it's not so important the exact difference, but it's important, I think, to remember that this runs under vacuum, no nasty chemicals used in making these coatings. Kind of a sister process is called plasma-assisted chemical vapor deposition. In the former slide, I showed you that we started with a solid, a metal. In this case, we actually deposit out of the gas phase only. So the precursors are either a gas or a liquid that get into the vacuum chamber. We ignite the plasma sheet over the products that are on the substrate table again. And in this plasma sheet, the gases will be cracked and form coatings by reacting with other gases and making that way the desired coating with the desired properties. Here's a short overview. There's many ways of creating the PVD vapor flux. It's basically split in two blocks, sputtering and evaporation, as I showed you in the overview. And there's different ways basically to evaporate a metal or to sputter a metal. I don't go in detail. As you can see, there's many ways to create this vapor flux, as mentioned before. Then diving a little bit in the title of this and the topic of discussion for this presentation, where actually these PVD coatings contributing to a sustainable economy. I'm going to split it in a few blocks where I have identified some, and as you will see in my conclusions, I don't going to have the claim that is covering all the, let's say, possible solutions where PVD is used to have a sustainable impact. It's just examples in this case. There's many more, but after today's presentation, I'd like you to have a feel that it is widespread use of it. So if you look at PVD coatings on manufacturing tools, why are they, let's say, sustainable and contributing to society in that sense? It is giving us increased productivity, higher speeds, and in the case of cutting tools, also higher feeds. So the productivity goes up, but also there will be less tool changeover, let's say, to replace tools. That makes it also more efficient. Better quality of parts. So with higher first pass yields in production, there will be not, let's say, secondary processing and more raw materials used and energy being consumed to make these parts. So we get a better surface finish quality with these coatings, with the use of these coatings. Another example is better mold release of parts if you talk about and think about plastic injection molding applications. We can also do stripping and recoating. So the same tool can be used multiple times. So in that way, we save raw material use and processing energy. So instead of making a tool over and over new tools, we use the same tool again. And that typically can be up to about 10 times, depending on the use of the tool. We also reduce a lot the use of oil-based lubricants during the manufacturing. That's both for cutting applications, where we can go even, in some cases, totally dry, but also in forming tool applications to have, let's say, the parts follow the shape of the die and better flow by the use of coatings instead of oil-based lubricants. So that's also, I have some examples of that as well. Also, if you are totally oil-free, I don't mention it here, but also means there's less washing of these parts after machining, so less chemicals being used then in the supply chain as well. Some examples of productivity improvements. Here are some brand names. It's not so much in this case about the coatings that are being used in this plot, but it's more about the statement in the left bottom where we say, in this case, is only water-soluble oil used with 10 to 20% of concentration instead of 100% oil. So a tremendous reduction of oils used and contamination to the environment. Another totally dry machining. This is hobbing application, where you see the number of parts produced going in several thousands with one tool, and this is to produce gears. Another one is also dry machining. This is for micro end mills. Another one where one of let's say our coatings, our portfolio is improving the productivity over a standard solution about a factor 2, and again totally dry. So the standard is using oil lubrication. We have no use of lubricants and have still a factor 2 almost in productivity in the number of pieces produced. What is also what I mentioned important is stripping, sometimes regrinding and recoating of the same tool. So again, I repeat myself, no extra materials, raw materials necessary. In this plot on the right hand side, you see a comparison of a reworked end mill compared to a new end mill. And it's pretty much an overlay of the number of, let's say, of the energy used in this cutting experiment, or actually not an experiment, in production, and the number of milling passes. So you see, very comparable and a very way to support the environment by reusing tools. Another away from cutting applications, more into forming tool applications. Here we see an example where we use PVD technology over a CVD. CVD stands for chemical vapor deposition, and it's a very high temperature process. 800 to 1000 degrees or even up to 1200 degrees Celsius is the typical processing temperature. We found a coating solution by PVD. On the right hand side, there's a trade name Ironbond 90 in this case, where we saw also here a factor 2 of an improvement over the CVD. But in the, let's say, sustainability thinking, we process this coating at 450 degrees Celsius instead of 1000, so about half the temperature. So the energy consumption is much lower, and it isn't mentioned here, but also the processing time is typically for CVD about 24 hours at this temperature, where we process about 6 to 8 hours. So there's another, let's say, gigantic savings in CO2 footprint in processing these coatings. Here you see also self-lubricating solid films in use. On the right-hand side, you see the workpiece. There's no need for phosphating the workpiece, and there's also no longer a use for mineral oils in this specific example of dry forming. What we also see in the automotive industry, in the forming business, a much higher use of high-strength aluminum materials. Of course, in the global automotive engineering, the trend is to go lightweight, to save fuel and have lower emissions for passenger cars, but also for trucks, of course. It started a lot with Ford F-150 truck, and we've been working with that team since 2015 to find solutions for good cold forming of aluminum sheets to form the body panels of this truck. You see here an example of a coated die on the right-hand side and the magnification of a coating architecture that was deposited by PVD. The coating thickness is around 5 micrometers in total, just to get you a feel for how thin these coatings actually are. In that sense is also good because they don't change the tolerances of a very nicely designed die. So the die tolerances will be, let's say, maybe 0.05 of millimeter, but we are certainly an order of magnitude lower in our coating thickness. But in this typical application, forming of aluminum can be forming a challenge, more so than forming steel. And that's mainly because the aluminum tends to stick at the tool, and that needs a lot of nasty cleaning steps to keep the tool, let's say, in production, but also gives a lot of scrap pieces and cracks in the aluminum if you try to form it, let's say, with a classic design tool without coatings. The abrasion resistance is also key. The aluminum is not just aluminum, it typically contains silicon particles as well to get the strength into the aluminum sheet materials. And that will also contribute to excessive wear on the die. But this hard I-1 42 coating with a DLC, diamond-like carbon top coating, is also resistant against abrasion. Okay. Here you see actually a comparison of this coating on the work PC aluminum alloy. Failure mechanism used to be adhesion and a sticking failure, as I explained on the last slide. Yeah, it's a little bit crude to say it's a 500% increase. I rather say basically the parts being produced are now, let's say, in the thousands instead of almost none with an uncoated tool. Scrap rate tremendously reduced, so do it right the first time. And the use of coatings have in this slide also shown that yeah, the almost total elimination of scrap parts, so minimizing the energy consuming recycling of aluminum and a substantial reduction of the CO2 footprint by using PVD related coatings. You can imagine if you have an expensive die, they can easily be 10,000 of euros, US dollars, whatever currency you're working in. But you see here the very nicely defined shape of such a die, which can be even up to 1 by 1 meters or even bigger. With all these nice features in the tool surface, you want to keep as a feature, of course, and the coatings protect to lose these features. So your products will also have, let's say, the imprint of this feature in their in the final shape. That's the goal of such a tool. And we have here an example where we strip the coating and we keep the features and we recoat after polishing these dies, so to give them a second, third, or even fourth life. And again, some of these expensive tools, yeah, with a couple of $1,000 of a coating get a new life. And of course, you will understand that is a considerable contribution to the reduction of CO2 footprint. We're also helping in our industry to switch from gas nitriding to plasma nitriding. On the left side, you see, let's say, features of gas nitriding. On the right-hand side, plasma nitriding features. But if you look, let's say, with respect to the environment, we see a decrease of energy needed in the processing of these coatings. But also, what is also important, less harmless gases are being used in the plasma nitride version, and the environment gets a better protection in that way. So I give you some examples of tools helping out, but also mechanical components are being helped in many cases over many past years and also in the future to come. So how is that done, let's say, in one slide as a major overview? Reduction of friction losses in moving machine elements. And I also see a car as a machine in that sense. So we have helped many applications here. Enabling high temperature applications. Think about turbines and also aircraft engine being a turbine in that sense. Corrosion protection, longer life, with less corrosion products that go into the environment. With the longer life of the machine parts, you see extended warranties on cars, for example, longer life of parts. Use of lighter base metals, aluminum instead of steel, we see also more and more use of light titanium materials. Instead of, let's say, changing the materials, you could stick with steel that may make it smaller because you have higher power densities that you can run through these parts because of the higher load bearing capabilities that coatings offer. Also, the reduction of hexavalent chromium, which is pretty nasty in its manufacturing process, not so much in the end use, but especially during the electroplating process itself. And we have also more and more examples coming into play where PTFEs are being replaced by vacuum deposited coatings. Some examples. Over the years, we see the average fuel consumption per 1,000 kilogram vehicle weight coming down for both petrol and diesel. Of course, diesel is phasing out as we speak, as in this presentation here. But still, the motivations are climate change, reduction of greenhouse gases, stronger emission legislations that we have seen every so many years, and increasing energy and fuel prices. So what do we see in the market trend for automotive? Engine downsizing, high pressure direct fuel injection systems have come in and actually are still increasing today. Start-stop systems, which give more wear situations where coatings help out. Hybrid vehicles. So you have electrical portion, but still you have an combustion engine that is running. Although they are smaller, they're still combustion engines that need coatings. Full 100% electric vehicles, and as mentioned before, you have increased warranty and service periods expectations. Some examples that are still coated today out of that mix: piston pins, piston rings, valve tappets, all kind of cam followers, rocket arm shafts. The combustion engine fuel injection components, the control pistons, the plungers, the needle valves, and some pump components themselves and orifices. Not so directly here, car body components for decorative purposes, but also functional. I show here on the right-hand side, there's actually a door lock mechanism that we've been coated since 2002, and that eliminated the grease necessary on the door lock for the locking mechanism of a car door. Fuel injection has been big since mid-90s, especially in these years. The diesel, they went up to pressures, injection pressure of over 2000 bars, and the best heat-treated steel didn't survive these needs. So that's where the diamond-like carbon coatings were coming in play and helped out this technology even up to date. And we see here an example of the HDP 6 pump source for Bosch. That's a new system where they use so-called TAC carbon-based coatings, and this pump pressure goes to 300 bars for gasoline. We also see more and more actually hydrogen coming into play. That's the next step where hydrogen injection systems are, let's say, being designed as we speak. But in this case, in this example, we see a fuel efficiency improvement of 1 to 3%, which is enormous in this marketplace. Other examples you see here in a cut open version of an engine. You recognize for yourself tappets, valves, piston rings, connecting rods, etc. Zooming in a little bit on tappets in this case. These are coated tappets with diamond-like carbon top coating, mass production. There's different coating types, not go into detail here, but they improve the wear resistance, so the life of a tappet. They reduce the friction tremendously. I showed it on the next slide. And by reducing the friction, it also has reduced a lot of CO2 emission levels. Here is the source from Ford, actually, this graph. But you see on the valve train, quite tremendous losses in the valve train. The tappet is part of that, colored blue on the left-hand side. And I showed you the coated tappet that's coated on the top in contact with the camshaft. You see here the trend where the DLC, the diamond-like carbon coatings, reduce the friction between the tappet and the camshaft by about 40 to 45%, and giving us this this enormous reduction of energy and fuel in that sense. This is not stopping here. What is also happening, it's the oils are changing. Let's say the viscosity is changing, more and more, let's say, low viscosity oils, and that's actually again an impact on the mechanical components in the combustion engine, where coatings are helping out to survive under these, let's say, more extreme mechanical conditions and friction and wear situations, and that's also developing ongoing. Other examples in our automotive piston rings. This is from a company, Tenneco, pulled it from the website, but also here you see these coatings, diamond-like carbon. It's on the top, the thickness of about 10 micrometer. They reduce wear and scuffing. They also reduce the coefficient of friction, and in that sense, improve fuel consumption levels and CO2 emissions again. Here it's a claim that It's economy, the fuel economy saving is 1.5%, and an equivalent of CO2 reduction of 3 grams per driven kilometer and for light vehicles. Here's some specs of these coatings, but that's again, we're not going into technical details, more let's say the impact. By experience, I can say in many cases, these coatings used to be electroplated chromium 6, so the nasty hexavalent chromium 6 plus was used here, and that's also in that sense a replacement of that technology in parallel. So it's also direct environment impact, but also indirect by the better performance of the engines. Another example here, it's a frictionless gas lubricated crankshaft seal from company Freudenberg. They call it Levitex in the trademark, where they also have reduced the CO2 emissions by using DLC coatings. You see here some of the data, and the emission reduction is stated as 0.5 to 1 gram CO2 per driven kilometer, and virtually nowhere, so long life in a car engine. Looking in the future, we all know, and I see more and more full electrical cars coming on the road. Here's a coated differential pin in the transmission of the Porsche Taycan, coated also by a DLC family related coating. I think I have the next page. Also here some vision from Mercedes-Benz, where they also see more and more use of coatings actually indirectly, because the energy consumption has to come down to about, their target is 8.7 kilowatt hours per 100 kilometers driving. But all in all, it comes down basically to efficiency improvements, and also in parallel noise reductions if you go full electric. And here there's a great future also for low friction, low wear coatings in 100% electric cars. Other examples, coatings for components and off-road diesel engines, still used quite a bit. On the right-hand side, here's a connecting rod, which is about close to, I think, 60, 70 centimeters. And you see the piston pin that's in here, coated also with diamond-like carbon. We eliminated actually the bronze bushing, which used to be in this position here. You see the yellow. So besides friction reduction, it also eliminated the complete component in this assembly. On the left-hand side, you see the turbochargers, where also DLC coatings offer wear protection and longer life in this example. Another complete different example, the use of PVD coatings. It's heat reflecting glass. I think we all have heard about HR plus, double plus and triple plus layered glass in combination with noble gas in between the glass plates. But the deposition of heat reflecting coatings is being done today, various sizes of glass by means of inline PVD coatings systems. Here's one example of company Von Ordane, where the glass goes in on one side and comes out on the other side. This is a vertical system, but you have also horizontal placed machines where PVD layers are making the heat reflecting coatings. A little bit more in detail here. You see either 2 or 3 layers of layered glass in combination with the noble gas and the vacancy in between the glasses. But you see also the deposition of the heat reflecting PVD coatings, and they lead to conservation of warmth and heat in the winter, but also keep the rooms cool in the summertime. So decreasing the heating and cooling, and therefore improved energy balance of buildings. I don't think I tell you anything new in today's situation. It's in the news every day, where we have to conserve energy in our houses and in our buildings. Another example that's also already originating from the mid-90s in the decorative field, but that's not just for the looks, but also for wear resistance. But decorative PVD coatings have been replacing electroplated brass. And in the old days, a fixture for your bathroom was plated with nickel layers, nickel chromium layers actually, sometimes copper nickel chromium, but then there was a plated brass for the looks with a lacquer. This is all replaced now by PVD technology, zirconium carbonate coating in this case, and the lacquer layer was also eliminated. I think from the past, when you were visiting a hotel room, you could see, let's say, the wear through of, let's say, brass plated fixtures, and you were looking on the nickel, looking, let's say, pretty nasty. Today, you don't see that anymore with the wear-resistant PVD coatings. If you say, I want to eliminate also the nickel plating underneath the PVD in this example, you can go to full stainless steel with PVD only and have a full elimination of the plating technology with the nasty chemicals involved. See many different colors and their color ranges and color coordinates. Again, technology that we skip today. Other examples, besides the faucet industry, you see replacement of stainless steel and other metal parts by plastics, also in cars to make them, of course, light again. So reduction of weight and fuel consumption will be also lowered indirectly. So you see many more, let's say, interior components that are ABS plastic or other plastics coated by PVD. Other examples is that we reproduce or are pretty close in reproducing gold colors. So instead of using real gold, we make ceramic materials that look like golds on faucets and fixtures. So it's cheaper, but also less mining involved when we, let's say, make fake gold, and it's also more wear resistance. You see it, for example, on slot machines in Las Vegas as well. Our sister company has developed a trade name CROMATIPIC, another example of replacement of electroplating on plastics. It started mainly for the automotive industry, for emblems, etc. But you see on the left-hand side, the old, let's say, technology, and still being used, unfortunately, a lot today, but as pressure by electroplating materials to get your chrome finish that you see on cars. But the sister company Hauser has developed a lacquer alternative with a chromium layer, which is RoHS RoHS compliant and being introduced more and more in the automotive arena. Another nice example that we found is not being done at our company, but you see also PACVD silicon oxide coatings on the trays that go into dishwashers. And apparently it gives us less energy consumption when you're drying your load. So it makes it easier to vaporize the water of the load. Small things can help and go a long way if you do it every day. And this gives, let's say, a lift in the energy classification system for this. Where else do we see PVD coatings? PVD coating electrical components, EMI shieldings, laptops, mobile phones, for example, have these PVD coatings inside. Semiconductors, so the computer chips, they get higher capacities and get smaller and smaller over time. That's only possible because of smart PVD and CVD and ALD layering systems that, in that sense, making components smaller and lasting longer and have more, let's say, power helps indirectly also to the environment and the CO2 footprint. Also in manufacturing machines of chips, there's more and more use of PVD coatings to make that actually happening. So both optical, tribological, and there's even some examples of temperature protection. Smart sensors, we see more and more coatings on radar domes in cars, for example, in your rear view mirror, and wearable electronics could be your watches, your smart watches, for example, but there's more of these examples. So these are all enablers to contribute indirectly there as well. Where else? PVD coatings in the medical field. How do we help, let's say, society and the environment here? Anti-allergic implants actually increase the success rate of surgeries. A very high percentage of patients is allergic to metal ions, especially nickel ions. And there are in many metals today, actually. I get some examples, but coatings can help to get these nickel elements into the human bodies or actually in animal bodies as well. So it reduces the number of surgeries a lot, and also it reduces the patient's time in a hospital. So that makes it much more efficient for hospitals, and also more, let's say, nice for the patient in the end. Also, I have an example of lower contact temperatures during surgery because of coatings, and that reduces the killing of tissue and bone tissue, and it leads to faster recovery again. Also, anti-allergic coatings lead to less infections and also help in trauma situation. If somebody gets in an accident on the road, for example, and you have coated trauma implants, that can help the recovery and because of less infections immediately. Another one that's related is food processing. So if you have less abrasive wear on the, let's say, while processing food, that helps a lot. I have some examples, but you can think about the production of chips and potatoes, which is very abrasive, anti-sticking when you produce candy bars or pastas. And also you don't like oils and greases in your beers and milk. So we also have solutions that are solid lubricants instead of these oils and greases. Here you see the Medfin portfolio, improve implant durability. So a coated new implant has a life of about 30 years, and it's also increasing with, let's say, improving these coatings compared to an uncoated implant. So that's a factor 2. That means, there's less surgeries, factor 2. If you have to come back after 15 years or 30 years, that's a factor 2, and maybe you can have it for the rest of your life. But also, if you think in the other direction, younger patients can also get implants, so that also they can enjoy it early in their life, less pain, and pick up their lives earlier on if needed. I mentioned it before, but these type of coatings, as you see here on knee implants, they're also a barrier for metal ion leaching out of the base cobalt chromium base metals to the patient's body and causing issues through infections. Here's another example. Here you see some drills for drilling into bones. There was an experiment done where you see a comparison here, let's say in order of cutting holes in bones. And what is, let's say, the tip temperature and also then the bone temperature during the surgery. You see here uncoated, let's say in a range of 85 to 90 degrees Celsius developing and killing tissue. And with this coating, titanium nitride in this case on top, it goes to about 65 degrees Celsius. A tremendous advantage in the use of coatings and, let's say, more efficient surgery. Another example, we have coatings that reduce bacterial colonization, and in the testing up to 50% according to this ISO standard. So increase of performance, less downtimes, and improved safety for patients as well. Some food examples where the tools last longer, less production stops, but also less iron transfer from the tools to the food, which you don't like as a consumer either. You see here an example of pasta production where the tools, as identified in this overview here, are being coated or will be coated. Another example is sugar refining, which is very abrasive, as you can imagine. You see tools here in this component in an open version that are coated to reduce again, let's say, the loss of steel that goes into the sugar, but also to have longer life ultimately. Another example of pumping and processing liquids. This is for brewing. In this example, where you see a pump, it's not cut open, but components being coated with dry lubricants instead of greases. Then PVD coatings in correlation with renewable energies, a hot topic today. If you think about wind, there's coatings being used in transmission components in windmills, especially high up in the air. You want them to last. It's very difficult to do maintenance if you're 30 meters or higher up in the sky. Solar, I don't have examples here, but we all know photovoltaic cells including semiconductor-based photons to electricity conversion. So a lot of sputtered metals and transparent conductive oxides are being used in these solar panels today. They won't work without them. Hydrogen economy, I have some examples here, but the use of PVD coatings today in fuel cells and electrolyzers are being used. Even in nuclear power, you see use of coatings. One example, we coat, for example, valves in the water cooling systems. So there's no wear of these valve components and no water leaks because you don't want to have contaminated water leaking into the environment. Here's an example of bearings that go into windmills. You see them on the right-hand side. There's a roller bearing. These are huge components. They are tens of centimeters because the bearings are tall, of course, in windmills. The coatings are to improve the contact fatigue properties in this case. And you don't want to have so-called pitting issues in the tribological system. At Iron Bond, we also coat bipolar plates. For today's situation, we have two coatings as PVD carbon materials. Since we coat about PVD coatings, I focus on that one particularly here. You see here a load on the left-hand side of so-called bipolar plates coated with carbon. It's typically thin coatings in our book. It's 100 nanometer of base metal, typically with a 50 nanometer carbon coating that gives us the conductivity that we need, and also the corrosion protection in this very aggressive environment of a fuel cell. PVD coatings manufacturing itself, it's not just the impact of the coatings on the products, but of course we also have responsibility when manufacturing these coatings. If you look at PVD coatings for manufacturing, the main use actually for PVD coatings is electricity. So if you look on the impact, we are an electricity consumer. Why? Because we heat up parts in the process. Then we have to get these metals from a solid state into a vapor state when evaporating them. It costs energy. And after the process, we cool down the parts. And of course, we have these production facilities that are in buildings. So you have, let's say, the usual light and insulation, air conditioning involved in trying to save energy. How to reduce basically the processing kilojoule per part. That's basically a number you could say when you produce a coating on a part, how many kilojoules would you virtually take if you include everything? So what can we do? We can, of course, use renewable energies, produce our own renewable energies, or focus, let's say, on buying only renewable energies. Of course, then you can say, yeah, but then you push it to somebody else. But it's maybe better to, let's say, centralize this and have huge and effective factories making, let's say, wind energy or using solar energy and create electricity that Iron Bond can use, or Iron Bond and our, let's say, sister type of companies. Link heating and cooling sources in a factory. Like I mentioned, we cool parts, but also on the other hand, we heat up parts. We also heat up cleaning lines to wash parts prior to coating. So are there ways that we can use the cooling energy, basically, or the energy to cool parts to heat up other parts in the factory? We're also looking at lower PVD processing temperatures. I had an example before where we look at more use of PVD instead of CVD. When we process, can we squeeze more parts in a load so that we have a better transfer efficiency of the evaporated metals? Of course, also here, scrap. To do things 2 times or 3 times is never efficient. So focus on 100% first pass yields of parts in production. What can also help here is further digitalization of our manufacturing, including Industry 4.0. So coming to, let's say, the summary in this case, in my presentation. In short, PVD coatings have already been key enablers for sustainability for decades, and PVD coatings will continue to play an important role for going forward. I think we have only scratched the surface here. PVD coatings manufacturing can even be more energy friendly. That's also homework to be done at our end. Again, this presentation does not claim to be complete. It should give you a good insight on how PVD technology plays and will play an important role in further improving the sustainability and help our society in that sense. Thank you for your attention, and through the setup of this seminar, feel free to have some questions or suggestions. Thank you.
Thank you very much, Ton. I think that was an excellent presentation. I think you demonstrated very, very effectively the huge range of functionalities of PVD films, PVD technologies, and showed how it's an enabling technology for many, many other applications. And in a lot of cases, the general public is simply completely unaware of the technology behind the everyday consumer items that they're using. But it's driven by PVD technology, thin film technology. And as you say at the end there, going forward, I think I can only see the applications for PVD increasing as demands for films become, smarter, greater functionality, increased durability, all of these things. I think PVD will be around to answer many of those questions. So I think we do have talking about questions. We do have some from the audience. I'll just take them in the order that they came in. The first one is, what kind of porosity levels do you normally obtain in PVD coatings? Can this vary according to the material deposited?
The porosity level?
Yeah, porosity level.
Okay.
I know it can be very low, but it does depend a lot on the process, doesn't it?
Absolutely. It depends on the process. So the gas phase based coatings, the PACVD coatings tend to be more dense in general, more glass-like, but it also depends, let's say, on the formation of the material that you deposit in relation to the deposition temperature. They can be either more columnar or more amorphous. The columnar structures, I must admit, PVD coatings are typically deposited columnar, and there is, let's say, pathways between the surface of a coated product and the product before coating. So these are very tiny channels, so-called pinholes. They can cause some excess of corrosion media to the base metal that has been coated, but percentage-wise, this is still really low. It's still less than 1%, is my guess, if you would translate it in percentages. Extremely low, but I cannot say it's 100% not existing either. But again, it depends, like you said, Peter, what technology and what coating you are aiming for.
Yeah, and there are ways where if you needed a high porosity for a specific application, you could actually create a high porosity. So again, that's just the versatility of the PVD processes. Absolutely.
Sometimes, and it's a little bit a copy of porous nickel by electroplating. You can make, let's say, porous coatings on purpose. So you basically, rather than getting so-called pitting corrosion, you can spread the corrosion really thin that the naked eye won't see it. That's a little bit the similar trick. Also, we make porous coatings, for example, titanium PVD on peak metals in PVD, where you actually increase bone growth into the implant by a porous structure. So that sometimes, I'm glad you did bring it up, Peter, but yes, there are multiple examples where you actually like porosity.
Sure. Another question then, are heat reflective coatings being used in automotive windshields currently? Which I can confirm they are, but there's a lot of, again, there's a lot of variation in the products there, and some people are looking for things like de-icing. Some people are just looking to reduce heat loads into a vehicle.
Yeah, the answer is simple. Yes, it's I think pretty much in all cars.
Yes.
And they also run, let's say, in these inline coating machines. It's a smaller flat glass that's being coated, also with ITO coatings, as they call them. And then the glass windshields will be shaped actually afterwards. But that's also for the looks, of course. We see more and more cars where they like the dark tinted glass, but it's also a lot related to heat reflection. Absolutely.
That's that. You raised the point there about the change in the shape afterwards. That a lot of coated glass, and you mentioned architectural glazing for heat control, has to be able to survive a tempering process now, which has required redesigns in some cases, because some of the elements like the silver layers in low emissivity coatings, the silver is very mobile, and sodium is mobile in glass. So there's been a lot of redesign of these kind of coatings to suit the fact that they now need to be tempered in many cases. Another question, have you any experiences of coating cemented carbide tools for milling compacted pearlitic cast irons? What is the best coating nanolayer structure?
Yes, we coat cemented carbide substrates all day long, and we have a wide portfolio for cast iron. I must admit, we have so-called segment managers that are the specialists more than I am on the details. But typically, I would say my first guess would be chromium aluminum nitride type of coatings. Crosscut is our trade name in that direction, being used as a kind of a generic coating, including cast iron with the nodules and abrasive type of substrate material. But I would recommend to contact me then maybe separately, and I can give you 100% full answer through, let's say, our specialist. So I apologize to hold back, but we definitely have solutions, but I cannot say for 100% sure that's just the one and the only one.
Okay, here we go. Another one. What are the mandatory approvals needed for coating qualification when it comes to biomedical applications? Are the films designed to be porous to allow tissue growth, akin to hydroxyapatite coatings? We've already touched on that, but if you could perhaps, what are the mandatory approvals?
Yeah, it's full of FDA approvals. Sometimes it's a kind of, it's almost like a Me Too product. It's, I think they call it 501K, if I remember correctly, approvals. But that's typically in the hands of the OEMs of the implants, because it's, of course, the coating is only a small portion of the whole implant. We have, let's say, data sheets for ourselves. But yes, any implant that goes in a human body and even animals is running through lots of approval rounds.
Of course. Has your company quantified embodied kilowatt hours coming from the coating process? Do you have any data or methodology intended to link such embodied kilowatt hours with target consumption, life LCA, CO2 footprint of coated components? So life cycle analysis, CO2 footprints, carbon footprints, this kind of thing. So yeah, I guess the questioner is asking what data do you have on things like that?
Yeah, it's of course, like in any company, probably a hot topic. So we monitor, let's say, more and more machines on their energy consumption, very direct. As mentioned, also Industry 4.0 is going to help us a lot. So we still have a lot of items, let's say, on maintenance that are time-based, but we're going to use it more, let's say, data-based. Just simple chemical. If you have a certain alkaline tank, maybe in the past it was exchanged every week, just to be on the safe side. Now we're going to measure more data on the composition, the pH, for example, values, and you name them. And then it might be, let's say, that we're going to replace it every 2 weeks. But now it's still not, it's more time-based in some cases. Also, we are introducing more in situ plasma measurements, where we going to see, for example, when is the desorption of the parts really finished, instead of having it time-based. So then we can already go to the next processing step. Also for our so-called metal ion etching or ion etching steps, we can also see when is the surface ready for, let's say, absorbing a coating, instead of having it as time-based. But I think the biggest driver is having simple monitors, electricity monitors on cleaning lines, on coating machines, so that we see when are they actually taking most of the energy and what can we do about it. So the answer is yes, more and more of these tools are finding its way in our operations. And it's really important. It's a topic to identify basically, yeah, your bad guys and attack them one by one.
Absolutely. There's a related question from a second questioner. Could you comment on the sustainability of the manufacturing process, both on CO2 emission and chemical recycling? So a similar sort of question, really.
Yeah, again, we take pride to have a vacuum-based process. It's very clean in sense of chemicals. So there's not much going to waste in that sense. That's one part. That's why I mentioned in the explanation of the technology. What else can I say? The metals that we use are typically titanium or zirconium. So the leftovers they go to recycling. But again, I think our biggest problem is two items. It's electricity and alkaline chemicals. But the cleaning lines that we use prior to coating are wet chemical, and there's very little that goes actually into the drain. And maybe most of the typical washing machine at your house is maybe even more damaging than a huge industrial cleaning line that we run. So we look at these chemicals, a lot of filtering, and the PVD is mainly electricity.
Yes, it's got to be considered as far cleaner and greener than most other sort of surface engineering technology that's been around for years. So yeah, I think that's also going to be increasingly important. And the connection with the digitalization, well, Industry 4.0, I think that's something I've watched with interest over the last few years, and it's becoming increasingly important as well. Well, thank you very much, Tom. We have no further questions from the audience. Alan, if you'd like to say anything.
I would like to thank Tom again. That tremendous talk, Tom. Very, very insightful. And thanks again for doing it. Just to remind everybody that we do record these, so the talk is available on the network website. You have to join. You have to be a member of the network, and there's no charge for that. So I invite you to do that. I'd also like to remind you that we have Jorzik from Oerlikon Balzers this afternoon at 2 o'clock giving a webinar, and Jorg's going to talk particularly about PVD coatings in the automotive industry. So thanks very much to everyone for joining.